As an example to derivatives of polynomials, power functions, and the power down rule, we're going to next look at the derivative of the period of a pendulum. So in other words, we're going to look at how the period of a pendulum can be described as a function of the length of the pendulum, and then take the derivative of that function. So this was an observation that was first made by Galileo. He was, as the story goes, he was sitting in a cathedral or a church, and there was a chandelier that was rocking back and forth, and he was timing how long it would take to swing back and forth. And as the swings became less and less, he noticed that the period of the motion remained constant. So the period, the amount of time it takes to go back and forth, did not depend on how wide the swings were. And it turns out that the period only depends upon the length of a pendulum. So for example, if you have a pendulum like this, so you have some sort of fixed point up here, you have like a rod with a mass down here, and then this pendulum swings back and forth. So the period t, so this is the amount of time for it to go back and forth to do one complete revolution, is given by 2 pi times the square root of L over G. So where L is the length of the pendulum, and then G is acceleration due to gravity. So on Earth, that's 9.8 meters per second squared at sea level. So first of all, we can ask a question. Suppose you have a pendulum and a grandfather clock. How long does the rod have to be in order for the period to equal exactly 2 seconds? So suppose you want to build a clock construct a clock so that the period is exactly 2 seconds. Well, we set the period equal to 2, so we get 2 is equal to 2 pi square root of L over G. The 2's cancel, so I get 1 over pi squared is equal to L over G. So therefore, the length has to equal G over pi squared. So 9.8 meters per second squared divided by pi squared gives me a length of 0.9929 meters. So a pendulum with a length of approximately 1 meter will have a period of 2 seconds. So what we want to do next is look at the derivative of this function. So we want to compute dt dl. So here we have t of L is equal to 2 pi square root of L over G. So the derivative, we basically have L to the 1/2. So even though this G is on the inside, there are a few different ways you can look at this. The first is to say, well, G is just a constant, and this is the same as 2 pi over square root of G times the square root of L. So this is really just L to the 1/2. So T prime of L is going to equal 2 pi over 2 square root of GL. Now what did I do to figure this out? Well, the square root of L is equal to L to the 0.5. So when I take the derivative, the 0.5 comes down out front, so I get 0.5 L, and then I subtract 1 from the exponent, so it's L to the minus 0.5, which is the same as 0.5 is 1/2. The negative basically takes the reciprocal, and the 0.5 does the square root, so it's the reciprocal of the square root of L like this. And then I pulled the G and the L together. So basically T prime of L is just equal to pi over the square root of GL. Now this is the derivative of the period with respect to the length. So the units are going to be in seconds per meter. So the units of t prime are going to be seconds per meter, right? So if t prime of L, well, let's see, if the L is approximately 1, G is 9.8, 9.8 square root, take the reciprocal, multiply it by pi. So actually t prime of 1 is approximately 1.0035 seconds per meter, right? So this means that if the length of the pendulum is equal to 1, then an increase of 1 meter in the length should result in an approximate increase in the period of 1.0035 seconds. Though it might be too much to ask to say an increase of 1 meter of length, because here the length is only 1. So this might be a pretty far distance away from the current. So let's say, we be safe and say an increase of the length of 1 centimeter, right? So that's only a 1% increase in length. So this means that if the length of the rod were to increase by 1 centimeter, then the period will increase by approximately, so it's this times the change in L, so this times 0.01, 1 centimeter is equal to 0.01 meters, so by approximately 0.0010035 seconds. Actually, I put one too many zeros in there. So 0.01 seconds. So a 1 centimeter increase in the length of the rod will result in the period increasing by approximately 0.01 seconds. So that is the derivative. Now you can also take the derivative of this with respect to G. So here G, so to do that, so instead of viewing the pendulum and saying, well, how is the period affected by the length, we can say, well, how is the period affected by gravity? So it's the same formula, except it's just a slightly different interpretation. Instead of viewing gravitational acceleration as a constant, in other words, as a parameter, we treat the length as the parameter and G as the constant. So this would be suitable, for example, if you have a tall skyscraper and you have a grandfather clock and an elevator. Now the clock has a specific pendulum rod with a specific length. Let's say the length is 1 meter. So, but as you move from the ground floor to the top of the skyscraper, you're going to have a slight change in the gravitational acceleration. Not that it would be noticeable, but you might ask the question, well, how much will the period change if I'm at, if I put this pendulum clock at the top of a mountain versus at sea level, right? So there at the top of a mountain, your gravitational acceleration will be a little bit different. So let's clear some space. Okay, so basically now we can think of t as a function of g. So let's just think of, in fact, let's say the length is equal to 1 meter. So let's just view a particular grandfather clock with a pendulum of length of 1 meter, so that at sea level it should have a period of very close to 2 seconds. So basically t of g becomes 2 pi over the square root of g. So 9.8 square root reciprocal times 2 times pi. So the period t of g t of 9.8 is going to be 2.007089923 seconds. So that's the period of this grandfather clock when it's at sea level. Now, if we want to look at the period at a different altitude or figure out how much it's changing, well, first of all, we have to figure out that the acceleration due to gravity is going to depend on the altitude. So it's going to equal the acceleration due to gravity at sea level, I'll call that g sub 0, and then times the radius of the Earth divided by the radius of the Earth plus the altitude, quantity squared. Now this follows because gravity follows an inverse square law. So basically, the force due to gravity is given by capital G m over r squared, where r is the distance between a body and between the centers of the two bodies. The two m's are the masses of the two bodies, and g is Newton's constant of acceleration. So the acceleration is just going to be, on Earth, is just gm over r squared. So g is Newton's gravitational constant, m is the mass of the Earth, and then if you use the radius of the Earth, you get the acceleration at sea level. So to find the, so for example, g at sea level is going to be capital Gm over the radius of the Earth squared. But the gravitational acceleration at a height h is going to be Gm over the radius of the Earth plus h squared, which is equal to the acceleration at sea level times the radius of the Earth squared divided by the radius of the Earth plus h squared. Right? Because when I multiply g at sea level, this equation, by the radius of the Earth squared, I'm going to cancel out that in the denominator. Then by dividing by the radius of the Earth plus h, I'm going to get this in the denominator. So you can see how this equation follows from Newton's law of gravitation. So it's just an easier way of expressing the acceleration due to gravity in terms of the sea level acceleration and the radius of the Earth and the altitude. So what should we do with this next? Well, we can look at just dt dg. So we can look at the derivative of the period of the pendulum with respect to gravity. So dt dg, since this is equal to 2 pi g to the minus 1/2, the minus 1/2 comes down. So we get 2 pi minus 1/2, and then g to the minus 3/2. So that would be 1 over square root of g cubed. So the derivative of the period with respect to gravity looks like this. So negative pi over the square root of g cubed. So now let's ask a question. So let's say we have a sea level, and then we have a mountain with height of 3,500 meters. So using just the local linearization, in other words, using the tangent line approximation to this, in other words, using the derivative, let's approximate how much difference in the period of this pendulum we should expect between being at sea level and being at an altitude of 3,500 meters. So at sea level, g of sea level is 9.8 meters per second squared, and then g at an altitude of 3,500 meters, using the fact that the radius of the Earth is 6,378 kilometers, so that's 6,378 divided by 6,378 plus 3,500 meters is 3.5 kilometers. So that gives us a gravitational acceleration of 9.78925 meters per second squared. So basically the change in g is going to be this minus 9.8. So delta g is approximately negative 0.01075 meters per second squared. So that's the change in the gravitational acceleration between sea level and an altitude of 3,500 meters. Now dt dg at sea level, so t prime of 0, is going to be minus pi divided by 9.8 to the 3 halves. So t prime at 0, not at 0, at 9.8. So t prime at 9.8 is going to be minus 0.1024, approximately 0.25. So this would be seconds per acceleration due to gravity is meters per second squared. So seconds cubed per meter. So that is the approximate derivative of the period with respect to gravitational acceleration. And then we have the change in the gravitational acceleration. So what we can do is we can write the following. Okay, so the period when the gravitational acceleration is 9.78925 should be approximately the period of the pendulum when the gravitational acceleration is 9.8 plus t prime of 9.8 times the delta g, right, the change in gravitational acceleration. So this should be t of 9.8 was 2.007089925 plus t prime times delta g. Both t prime and delta g are negative, so we just have to multiply this by that. So multiplying t prime by delta g, we get 0.0011008 approximately. So basically, and when we divide this by 2.007, we get about a 0.05% change. So basically this divided by the initial period is approximately a 0.05% change. So going from sea level to an altitude of 3,500 meters would result in approximately a 0.05% change in the period of the pendulum. So you can ask yourself, I'll leave this for you to think about on your own, but given this, what we've worked out so far, let's say that the pendulum is calibrated so that it keeps track of time correctly when it's at sea level. So given the fact that the period of the pendulum is just slightly longer at an altitude of 3,500 meters, how long will it take before the pendulum is 1 second off? So how much time will go by before this slight difference in the period will accumulate to a 1 second error in the clock?